Now I wanted to give you a bit of an insight into the subtleties of how SQL compares timestamps and dates, because the results here can be a bit surprising. So I wrote 3 logical expressions here for you, and your job is to try to guess if either of these 3 expressions will be true or false. So take a look at them and try to answer that. As you can see, what we have here is a timestamp that indicates the 1st of September, 8 o'clock. Whereas here we have simply the indication of the date, the 1st of September. And the values are the same in all 3, but my question is, are they equal? Is this greater or is this smaller? So what do you think? I think the intuitive answer is to say that in the first case, we have September 1st on one side, September 1st on the other. They're the same day, so this ought to be true. Whereas here, we have, again, the same day on both sides, so this is not strictly bigger than the other one, so this should be false. And it is also not strictly smaller, so this would be false as well. Now let's run the query and see what's actually happening. Right, so what we see here is that we thought this would be true, but it's actually false. We thought this would be false, but it's actually true. And this one is indeed false. So are you surprised by this result, or is it what you expected? If you are surprised, can you figure out what's going on here? Now, what is happening here is that you are running a comparison between 2 expressions which have a different level of granularity. The one on the left is showing you day, hour, minutes, seconds, and the one on the right is showing you the date only. In other words, the value on the left is a timestamp, whereas the value on the right is a date. So different levels of precision here. Now, to make the comparison work, SQL needs to convert one into the other. It needs to do something that is known technically as implicit type coercion. What does it mean? Type is the data type, right? So either timestamp or date. Type coercion is when you take a value and you convert it to a different type. And it's implicit because we haven't asked for it, and SQL has to do it on its own behind the scenes. And so how does SQL choose which one to convert into the other? The choice is based on, let's keep the one with the highest precision and convert the other. So we have the timestamp with the higher precision on the left, and we need to convert the date into the timestamp. This is how SQL is going to handle this situation. It's going to favor the one with the highest precision. Now, in order to convert a date to a timestamp, what SQL will do is that it will add all zeros here. So this will basically represent the very first second of the day of this September 1st, 2012. Now, we can verify what I just showed you. I'm going to comment this line, and I'm going to add another logical expression here, which is taking the timestamp representing all zeros here and then setting it equal to the date right here. So what do we expect to happen now? We have 2 different types. There will be a type coercion, and then SQL will take this value on the right and turn it into exactly this value on the left. Therefore, after I check whether they're equal, I should get true here. Turns out that this is true, but I need to add another step, which is to convert this to a timestamp. And after I do this, I get what I expected, which is that this comparison here is true. So what this notation does in Postgres is that it does the type coercion, taking this date and forcing it into a timestamp. And I'll be honest with you, I don't understand exactly why I need to do this here. I thought that this would work simply by taking this part over here, but I also need to somehow explicitly tell SQL that I want this to be a timestamp. Nonetheless, this is the insight that we needed here, and it allows us to understand why this comparison is actually false. Because we are comparing a timestamp for the very first second of September 1st with a timestamp that is the first second of the 8th hour of September 1st, and so it fails. And we can also see why on this line the left side is bigger than the right hand side, and this one did not actually fool us, so we're good with that. So long story short, if you're just getting started, you might not know that SQL does this implicit type coercion in the background, and this dates comparison might leave you quite confused. Now I've cleaned the code up a bit, and now the question is, what do we need to do with the code in order to match our initial intuition? So what do we need to do such that this line is true and the second line is false, and this one is still false, so we don't have to worry about it? Well, since the implicit coercion turns the date into a timestamp, we actually want to do the opposite. We want to turn the timestamp into a date. So it will be enough to do the type coercion ourselves and transform this into dates. Like this. And when I run this new query, I get exactly what I expected. So now I'm comparing at the level of precision or granularity that I wanted. I'm only looking at the date. So I hope this wasn't too confusing. I hope it was a bit insightful, and that you have a new appreciation for the complexities that can arise when you work with dates and timestamps in SQL. Produce a list of member names with each row containing the total member count. Let's look at the expected results. We have the first name and the surname for each member, and then every single row shows the total count of members. There are 31 members in our table. Now, if I want to get the total count of members, I can take the members table and then select the count. And this will give me 31, right? But I cannot add first name and surname to this. I will get an error, because count star is an aggregation, and it takes all the 31 rows and produces a single number, which is 31, while I'm not aggregating first name and surname. So the standard aggregation doesn't work here. I need an aggregation that doesn't change the structure of my table and that works at the level of the row. And to have an aggregation that works at the level of the row, I can use a window function. And the window function looks like having an aggregation followed by the keyword over and then the definition of the window. So if I do this, I get the count at the level of the row. And to respect the results, I need to change the order a bit here. And I get the result that I wanted. So a window function has these two main components, an aggregation and a window definition. In this case, the aggregation counts the number of rows, and the window definition is empty, meaning that our window is the entire table. And so this aggregation will be computed over the entire table and then added to each row. There are far more details about window functions and how they work in my mental models course. Produce a numbered list of members ordered by their date of joining. So I will take the members table and I will select the first name and surname. And to produce a numbered list, I can use a window function with the row number aggregation. So I'll say row number over. So row number is a special aggregation that works only for window functions. And what it does is that it numbers the rows monotonically, giving a number to each, starting from 1 and going forward. And it never assigns the same number to 2 rows. And in the window, you need to define the ordering for the numbering. So what is the ordering in this case? It's defined by the join date. And by default, it's ascending. So that's good. And we can call this row number. And we get the results we wanted. And again, you can find a longer explanation for this with much more detail about window functions and row number in the mental models course. Output the facility ID that has the highest number of slots booked again. So we've already solved this problem in a few different ways. Let's see a new way to solve it. So we can go to our bookings table and we can group by facility ID, and then we can get the facility ID in our select, and then we could sum on slots to get the total slots booked for each facility. And since we're dealing with window functions, we can also rank facilities based on the total slots that they have booked. And this would look like rank over order by sum slots descending. And we can call this RK for rank. And if I order by sum slots descending, I should see that my rank works as intended. So we've seen this in the mental models course. You can think of rank as deciding the outcome of a race. So the person who did the most in this case gets rank 1, and then everyone else gets rank 2, 3, 4. But if there were two candidates that got the same score, the highest score, they would both get rank 1 because they would both have won the race, so to speak. And the rank here is defined over the window of the sum of slots descending. So that is what we need. And next, to get all the facilities that have the highest score, we could wrap this into a common table expression and then take that table and then select the facility ID, and we can label this column total. Then we will get total and filter for where ranking is equal to 1. And we get our result. Aside from how rank works, the other thing to note in this exercise is that we can define the window based on an aggregation. So in this case, we are ordering the elements of our window based on the sum of slots. And if we look at our map over here, we can see that we get the data, we have our group by, we have the aggregation, and then we have the window. So the window follows the aggregation, and so based on our rules, the window has access to the aggregation and it's able to use it. Rank members by rounded hours used. So the expected results are quite straightforward. We have the first name and the surname of each member. We have the total hours that they have used, and then we are ranking them based on that. So the information for this result, where is it? We can see that it's in the members and bookings tables. And so we will need to join on these two tables. Members mems, join bookings book on mem ID. And that's our join. Now we need to get the total hours, so we can group by our first name, and we also need to group by the surname because we will want to display it. And now we can select these two columns. And we need to compute the total hours. So how can we get that? For each member, we know the slots that they got at every booking. So we need to get all those slots, sum them up. And every slot represents a 30-minute interval, right? So to get the hours, we need to divide this value by 2. And remember, if I take an integer, like sum of slots, and divide by 2, which is also an integer, I'm going to have integer division. So I won't have the part after the comma in the result of the division, and that's not what I want. So instead of saying divide by 2, I will say divide by 2.0. So let's check how the data looks like. This is looking good now, but if we read the question, we want to round to the nearest 10 hours. So 19 should probably be 20. 115 should probably be 120 because I think that we round up when we have 15, and so on, as you can see here in the result. So how can we do this rounding? Well, we have a nifty round function, which as the first argument takes the column with all the values, and the second argument we can specify how do we want the rounding. And to round to the nearest 10, you can put -1 here. So actually, let's keep displaying the total hours as well as the rounded value to make sure that we're doing it correctly. So as you can see, we are indeed rounding to the nearest 10. So this is looking good. And to understand the reason why I used -1 here and how the rounding function works, I will have a small section about it when we're done with this exercise. But meanwhile, let's finish this exercise. So now I want to rank all of my rows based on this value here that I have computed. And since this is an aggregation, it will already be available to a window function, right? Because in the logical order of operations, aggregation happens here, and then windows happen afterward, and they have access to the data from the aggregation. So it should be possible to transform this into a window function. So think for a moment of how we could do that. So a window function has its own aggregation, which in this case is a simple rank. And then we have the over part, which defines the window. And what do we want to put in our window? In this case, we want to order by, let's say, our rounded hours. And we want to order descending because we want the guest, the member with the highest hours, to have the best rank. But clearly, we don't have a column called rounded hours. What we have here is this logic over here. So I will substitute this name with my actual logic. And I will get my actual rank. And now I can delete this column here that I was just looking at. And I can sort by rank, surname, first name. Small error here, I actually do need to show the hour as well. So I need to take this logic over here again and call these hours. And I finally get my result. So to summarize what we are doing in this exercise, we're getting our data by joining these two tables, and then we're grouping by the first name and the surname of the member, and then we are summing over the slots for each member, dividing by 2.0 to make sure we have an exact division, and using the rounding function to round down to the nearest hour. And so we get the hours. And we use the same logic inside a window function to have a ranking such that the members with most hours get rank of 1, and then the one with the second most hours get rank of 2, and so on, as you can see here in the result. And I am perfectly able to use this logic to define the ordering of my window, because window functions can use aggregations, as seen in the logical order of SQL operations here, because window functions occur after aggregations. And that's it. Then we just order by the required values and get our results. Now here's a brief overview of how rounding works in SQL. Now rounding is a function that takes a certain number and then returns an approximation of that number, which is usually easier to parse and easier to read. And you have the round function, and it works like this. The first argument is a value, and it can be a constant, as in this case, so we just have a number, or it can be a column, in which case it will apply the round function to every element of the column. And the second argument specifies how we want the rounding to occur. So here you can see the number from which we start, and the first rounding we apply has an argument of 2. So this means that we really just want to see two numbers after the decimal. So this is what the first rounding does, as you can see here. And we round down or up based on whether the values are equal or greater than 5, in which case we round up, or smaller than 5, in which case we round down. So in this first example, 2 is lesser than 5, so we just get rid of it. And then we have 8. 8 is greater than 5, so we have to round up. And so when we round up, this 79 becomes an 80. And this is how we get to this first round over here. Then we have round with an argument of 1, which leaves one place after the decimal, and which is this result over here. And then we have round without any argument, which is actually the same as providing an argument of 0, which means that we really just want to see the whole number. And then what's interesting to note is that the rounding function can be generalized to continue even after we got rid of all the decimal part by providing negative arguments. So round with an argument of -1 really means that I want to round this number to the nearest 10. So you can see here that from 48,292 we end up at 48,290, going to the nearest 10. Rounding with a value of -2 means going to the nearest 100. So 290, the nearest 100 is 300, right? So we have to round up. And so we get this. -3 means round to the nearest 1,000. So if you look at here, we have 48,300. And so the nearest 1,000 to that is 48,000. -4 means the nearest 10,000. So given that we have 48,000, the nearest 10,000 is 50,000. And finally, round -5 means round to the nearest 100,000. And given that we have 48,000, the nearest 100,000 is actually 0. And from now on, as we keep going negatively, we will always get 0 on this number. So this is how rounding works in brief. It's a pretty useful function. Not everyone knows that you can provide it negative arguments. Actually, I didn't know. And then when I did the first version of this course, commenter pointed it out. So shout out to him. Don't know if he wants me to say his name. But hopefully now you understand how rounding works and you can use it in your problems. Find the top 3 revenue generating facilities. So we want a list of the facilities that have the top 3 revenues, including ties. This is important. And if you look at the expected results, we simply have the facility name and a bit of a giveaway of what we will need to use, the rank of these facilities. So there's this other exercise that we did a while back, which is find the total revenue of each facility. And from this exercise, I have taken the code that allows us to get to this point where we see the name of the facility and the total revenue for that facility. And you can go back there to that exercise to see in detail how this code works. But in brief, we are joining the bookings and facilities tables, and we are grouping by facility name, and then we are getting that facility name. And then within each booking, we are computing the revenue by taking the slots and using a case when to choose whether to use guest cost or member cost. And so this is how we get the revenue for each single booking. And now, given that we grouped by facility, we can sum all of these revenues to get the total revenue of each facility. And this is how we get to this point. Given this partial result, all that's left to do now is to rank these facilities based on their revenue. So what I need here is a window function that will allow me to implement this ranking. And this window function would look something like this. I have a rank, and why is rank the right function even though they sort of gave it away? Because if you want the facilities who have the top revenues, including ties, you can think of it as a race. All facilities are racing to get to the top revenue. And then if 2 or 3 or 4 facilities get that top revenue, if there are more in the top position, you can't arbitrarily say, oh, you are first and they are second. You have to give them all the rank 1 because you have to tell them, recognize that they are all first. So these type of problems call for a ranking solution. So our window function would use rank as the aggregation, and then we need to define our window. And how do we define our window? We define the ordering for the ranking here. So we can say order by revenue descending, such that the highest revenue will get rank 1, the next highest will get rank 2, and so on. Now, this will not work because I don't have the revenue column, right? I do have something here that is labeled as revenue, but the ranking part will not be aware of this label. However, I do have the logic to compute the revenue. So I could take the logic right here and paste it over here. And I'll add a comma. Now, this is not the most elegant looking code, but let's see if it works. And we need to order by revenue descending to see it in action. And if I order by revenue descending, you can in fact see that the facility with the highest revenue gets rank 1, and then it goes down from there. So now I just need to clean this up a bit. First, I will remove the revenue column, and then I will remove the ordering. And what I need here for the result is to keep only the facilities that have rank of 3 or smaller, so ranks 1, 2, 3. And there's actually no way to do it in this query, so I actually have to wrap this query into a common table expression and then take that table and say select star from T1 where rank is smaller or equal to 3, and I will need to order by rank ascending here, and I get the result I needed. So what happened here, we built upon the logic of getting the total revenue for each facility, and again we saw that in the previous exercise. And then what we did here is that we added a rank window function, and within this rank we order by this total revenue. So this might look a bit complex, but you have to remember that when we have many operations that are nested, you always start with the innermost operation and move your way up from there. So the innermost operation is a case when, which chooses between guest cost and member cost and then multiplies it by slots. And this inner operation over here is calculating the revenue for each single booking. The next operation is an aggregation that takes that revenue for each single booking and sums these revenues up to get the total revenue by each facility. And finally, the outermost operation is taking the total revenue for each facility and it's ordering them in descending order in order to figure out the ranking. And the reason all of this works, we can go back to our map of SQL operations. You can see here that after getting the table, the first thing that happens here is the group by and then the aggregations. And here is where we sum over the total of revenue. And after the aggregation is completed, we have the window function. So the window function has access to the aggregation and can use them when defining the window. And finally, after we get the ranking, we have no way of isolating only the first 3 ranks in this query, so we need to do it with a common table expression. And if you look here, back to our map, this makes sense because what components do we have in order to filter our table, in order to only keep certain rows? We have the where, which happens here very early, and we have the having, and they both happen before the window. So after the window function, you actually don't have another filter, so you need to use a common table expression. Classify facilities by value. So we want to classify facilities into equally sized groups of high, average, and low based on their revenue. And the result, you can see it here. For each facility, it's classified as high, average, or low. And the point is that we decided at the beginning that we want 3 groups, and this is arbitrary. We could have said we want 2 groups or 5 or 6 or 7, but we have 3. And then all the facilities that we have are distributed equally within these groups. So because we have 9 facilities, we get 3 facilities within each group. And I can already tell you that there is a special function that will do this for us. So we will not go through the trouble of implementing this manually, which could be pretty complex. So I have copied here the code that allows me to get the total revenue for each facility. And we have seen this code more than one time in past exercises. So if you're still not clear about how we can get to this point, check out the previous exercises. So what we did in the previous exercise was rank the facilities based on the revenue. And how we did that is that we took the ranking window function and then we defined our window as order by revenue descending. Except that we don't have a revenue column here, but we do have the logic to compute the revenue. So we can just get this logic and paste it in here. And when I run this, I will get a rank for each of my facilities where the biggest revenue gets rank 1 and then it goes up from there. Now the whole trick to solve this exercise is to replace the rank aggregation with an entile aggregation and provide here the number of groups in which we want to divide our facilities. And if I run this, you see that I get what I need. The facilities have been equally distributed into 3 groups, where group number 1 has the facilities with the highest revenue, and then we have group number 2, and finally group number 3, which has the facilities with the lowest revenue. And to see how this function works, I will simply go to Google and say Postgres entile. And the second link here is the Postgres documentation, and this is the page for window functions. So if I scroll down here, I can see all of the functions that I can use in window functions, and you will recognize some of our old friends here: row number, rank, dense rank, and here we have entile. And what we see here is that entile returns an integer ranging from 1 to the argument value, and the argument value is what we have here, which is the number of buckets, dividing the partition as equally as possible. So we call the entile function and we provide how many buckets we want to divide our data into, and then the function divides the data as equally as possible into our buckets. And how will this division take place? That depends on the definition of the window. In this case, we are ordering by revenue descending. And so this is how the entile function works. So we just need to clean this up a bit. I will remove the revenue part because that's not required from us. And I will call this entile quite simply. And now I need to add a label on top of this entile value, as you can see in the results. So to do that, I will wrap this into a common table expression. And when I have a common table expression, I don't need the ordering anymore. And then I can select from the table that I have just defined. And what do I want to get from this table? I want to get the name of the facility, and then I want to get the entile value with a label on top of it. So I will use a case when statement to assign this label. So case when entile equals 1, then I will have high. When entile equals 2, then I will have average, else I will have low, end the case and call this revenue. And finally, I want to order by entile, so the results are first showing high, then average, then low, and also by facility name. And I get the result that I wanted. So to summarize, this is just like the previous exercise, except that we use a different window function, because instead of rank, we use entile so that we can bucket our data. And in the window, like we said in the previous exercise, there's a few nested operations, and you can figure it out by going to the deepest one and moving upwards. So the first one picks up the guest cost or member cost, multiplies it by slots, gets the revenue for each single booking. The next one aggregates on top of this within each facility, so we get the total revenue by facility. And then we use this, we order by revenue descending. This defines our window. And this is what the bucketing system uses to distribute the facilities in each bucket based on their revenue. And then finally, we need to add another layer of logic. Here we need to use a common table expression so that we can label our percentile with the required text labels. Calculate the payback time for each facility. So this requires some understanding of the business reality that this data represents. So if we look at the facilities table, we have an initial outlay, which represents the initial investment that was put into getting this facility. And then we also have a value of monthly maintenance, which is what we pay each month to keep this facility running. And of course, we will also have a value of monthly revenue for each facility. So how can we calculate the amount of time that each facility will take to repay its cost of ownership? Let's actually write it down so we don't lose track of it. We can get the monthly revenue of each facility, but what we're actually interested in is the monthly profit, right? And to get the profit, we can subtract the monthly maintenance for each facility. So revenue minus expenses equals profit. And when we know how much profit we make for the facility each month, we can take the initial investment and divide it by the monthly profit. And then we can see how many months it will take to repay the initial investment. So let us do that now. And what I have done here, once again, I copied the code to calculate the total revenue for each facility. And we have seen this in the previous exercises, so you can check those out if you still have some questions about this. And now that we have the total revenue for each facility, we know that we have 3 complete months of data so far. So how do we get to this, to the monthly revenue? It's as simple as dividing all of this by 3, and I will say 3.0 so we don't have integer division, but we have proper division, you know? And I can call this monthly revenue. And now the revenue column does not exist anymore, so I can remove the order by. And here I can see the monthly revenue for each facility. And now from the monthly revenue for each facility, I can subtract the monthly maintenance. And this will give me the monthly profit. But now we get this error, and can you figure out what this is about? Monthly maintenance does not appear in the group by clause. So what we did here is that we grouped by facility name, and then we selected that, which is fine. And all the rest was aggregation. So remember, as a rule, when you group by, you can only select the columns that you have grouped by and aggregations. And monthly maintenance is not an aggregation, so in order to make it work, we need to add it to the group by statement over here. And now I get the monthly profit. And finally, the last step that I need to take is to take the initial outlay and divide it by all of the rest that we have computed until now. And we can call these months, because this will give us the number of months that we need in order to repay our initial investment. And again, we get the same issue. Initial outlay is not an aggregation, does not appear in the group by clause. And easy solution, we can just add it to the group by clause. So something is pretty wrong here. The values look pretty weird. So looking at all this calculation that we have done until now, can you figure out why the value is wrong? The issue here is related to the order of operations. Because we have no round brackets here, the order of operation will be the following. Initial outlay will be divided by the total revenue. Then it will be divided by 3.0. And then out of all of these, we will subtract monthly maintenance. But that's not what we want to do, right? What we want to do is to take initial outlay and divide it by everything else, which is the profit. So I will add round brackets here and here. And now we get something that makes much more sense, because first we execute everything that's within these round brackets and we get the monthly profit, and then all of it we divide initial outlay by. And then what we want to do is to order by facility name. So I will add it here. And we get the result. So quite a representative business problem, calculating a revenue and profits and time to repay initial investment. And overall, it's just a bunch of calculations starting from the group by that allows us to get the total revenue for each booking. We sum those revenues to get the total revenue for each facility, divide by 3 to get the monthly revenue, subtract the monthly expenses to get the monthly profit, and then take the initial investment and divide by the monthly profit, and then we get the number of months that it will take to repay the facility. Calculate a rolling average of total revenue. So for each day in August 2012, we want to see a rolling average of total revenue over the previous 15 days. Rolling averages are quite common in business analytics, and how it works is that if you look at August 1st, this value over here is the average of daily revenue for all facilities over the past 15 days, including the day of August 1st. And then this average is rolling by one day or sliding by 1 day every time, so that the next average is the same one, except it has shifted by 1 day because now it includes the 2nd of August. So let's see how to calculate this. And in here I have basic code that calculates the revenue for each booking, and I've taken this from previous exercises, so if you have any questions, check those out. And what we have here is the name of each facility and the revenue for each booking. So each row here represents just a single booking. So this is what we had until now, but if you think about it, we're not actually interested in seeing the name of the facility because we're going to be summing up over all facilities. We're not interested in the revenue by each facility, but we are interested in seeing the date in which each booking occurs because we want to aggregate within the date here. So to get the date, I can get the start time field from bookings, and because this is a timestamp, so it shows hours, minutes, seconds, I need to reduce it to a date. And what I get here is that for, again, each row is a booking, and for each booking I know the date on which it occurred and the revenue that it generated. Now for the next step, I need to see the total revenue over each facility within the date, right? So this is a simple grouping. So if I group by this calculation over here, which gives me my date, I can then get the date. And now I have compressed all the different occurrences of dates to unique values, right? One row for every date. And now I need to compress as well all these different revenues for each date to a single value. And for that, I can put this logic inside the sum aggregation as we have done before. And this will give me the total revenue across all facilities for each day. And we have it here. For the next step, my question for you is, how can I see the global average over all revenues on each of these rows? So that is a row level aggregation that doesn't change the structure of the table, and that's a window function, right? So I can have a window function here that gets the average of revenue over, and for now I can leave my window definition open because I will look at the whole table. However, revenue will not work because revenue is just a label that I've given on this column, but this part here is not aware of the label. I don't actually have a revenue column at this point. But instead of saying revenue, I could actually copy this logic over here, and it would work because the window function occurs after computing the aggregation, so the window function is aware of it. So this should work. And now for every row, I see the global average over all the revenues by day. Now for the next step, I would like to first order by date, ascending. So we have it here in order. And my next question for you is, how can we make this a cumulative average? So let's say that our rows are already ordered by date. And how can I get the average to grow by date? So in the first case, the average would be equal to the revenue because we only have one value. On the second day, the average would be the average of these two values, so all the values we've seen until now. On the third day, it would be the average of the first three values, and so on. How can I do that? The way that I can do that is that I can go to my window definition over here, and I can add an ordering, and I can order by date. But of course, the column date does not exist because that's a label that will be assigned after all this part is done. Window function is not aware of labels. But again, window function works great with logic. So I will take the logic and put it in here. And now you can see that I get exactly what I wanted. On the first row, I get the average is equal to the revenue. And then as it grows, we only look at the current revenue and all the previous revenues to compute the average. But we don't look at all of the revenues. So on the second row, we have the average between this revenue over here and this one over here. And then on the third row, we have the average between these three revenues and so on. Now you will realize that we are almost done with our problem. And the only piece that's missing is that right now, if I pick a random day within my dataset, say this one, the average here is computed over all the revenues from the previous days. So all the days in my data that lead up to this one, they get averaged and we compute this revenue. And what I want to do to finish this problem is that instead of looking at all the days, I only want to look 15 days back. So I need to reduce the maximum length that this window can extend in time from unlimited to 15 days back. Now, here is where it gets interesting. So what we need to do is to fine-tune the window definition in order to only look 15 days back. And with window functions, we do have the option to fine-tune the window. And it turns out that there's another element to the window definition which is usually implicit. It's usually not written explicitly, but it's there in the background. And it's the rows part. So I will now write rows between unbounded preceding and current rows. Row. Now, what the rows part does is that it defines how far back the window can look and how far forward the window can look. And what we see in this command is actually the standard behavior. Is the thing that happens by default, which is why we usually don't need to write it. And what this means is that it says, look as far back in the past as you can, look as far back as you can based on the ordering, and the current row. So this is what we've been seeing until now. And if I now run the query again after adding this part, you will see that the values don't change at all, because this is what we have been doing until now. So now, instead of unbounded preceding, I want to look 14 rows back plus the current row, which together makes 15. And if I run this, my averages change because I'm now looking, I'm now averaging over the current row and the 14 previous rows. So the last 15 values. And now what's left to do to match our result is to remove the actual revenue over here and call this revenue. And finally, we're only interested in values for the month of August 2012. So we need to add a filter, but we cannot add a filter in this table definition here, because if we added a where filter here, isolating the period for August 2012, can you see what the problem would be? If my data could only see revenue starting from the 1st of August, it wouldn't be able to compute the rolling average here, because to get the rolling average for this value, you need to look 2 weeks back, and so you need to look into July. So you need all the data to compute the rolling revenue, and we must filter after getting our result. So what that looks like is that we can wrap all of this into a common table expression, and we won't need the order within the common table expression anymore. And then selecting this, we can filter to make sure that the date fits in the required period. So we could truncate this date at the month level and make sure that it is equal, that the truncated value is equal to the month of August. And we have seen how date trunc works in the previous exercises. And then we could select all of our columns and order by date. I believe we may have an extra small error here because I kept the partial where statement. And if I run this, I finally get the result that I wanted. So a query that was a bit more complex, it was the final boss of our exercises. So let's summarize it. We get the data we need by joining booking and facility. And then we are getting the revenue for each booking. That is this multiply slots by either guest cost or member cost, depending on whether the member is a guest or not. This is getting the revenue within each booking. Then we are grouping by date, which you see over here, and summing all of these revenues that we computed so that we get the total revenue within each day for all facilities. Then the total revenue for each day goes into a window function, which computes an aggregation at the level of each row. And the window function computes the average for these total revenues within a specific window. And the window defines an ordering based on time, so the ordering based on date. And the default behavior of the window would be to look at the average for the current day and all the days that precede up until the earliest date. And what we're doing here is that we are fine-tuning the behavior of this function by saying, hey, don't look all the way back in the past, only look at 14 rows preceding plus the current row, which means that given the time ordering, we compute the average over the last 15 values of total revenue. And then finally, we wrap this in a common table expression and we filter so that we only see the rolling average for the month of August, and we order by date.